Okay, so for a continuous oriented fiber composite, with an applied load in the transverse direction of the fiber alignment. So the applied load is 90 degrees with respect to the fiber alignment. So if you have a composite and the fibers are aligned in this direction, the applied load is now 90 degrees from that. This is an isostress state in which the stress of the composite is equal to that of the matrix is equal to that of the fibers, and thus we'll just write that as sigma. And so now we can consider this isostress state and also write the strain of the composite is just the strain of the matrix times the volume fraction of the matrix in the composite plus the strain in the fibers times the volume fraction of the fiber. And so if we consider, let's say we take it as, here are the aligned fibers. If we take the strain of the fiber and here is the matrix, there will also be strain in the matrix, and we can consider the this case in which the stiffness can be considered as springs in a series. And so here, if these are spring, so this is for the fiber, and this is for the matrix. There's going to be some modulus of elasticity for each of the component, and we know that the strain is equal to stress divided by the modulus of elasticity, so thus we can rewrite this equation as stress in the system, in the composite, which is also stress in the matrix, which is also equal to stress in the fibers, divided by the modulus of elasticity of the composite with an applied load that's in the transverse direction T is equal to sigma divided by the modulus of elasticity for the matrix times the volume fraction of the matrix plus stress divided by the modulus of elasticity for the fibers times the volume fraction of the fibers. And so if we divide through by sigma, we get 1 over E sub CT and we also know that the volume fraction of the fiber plus volume fraction of the matrix has to both add up to 1, and so thus we can rearrange. Now we multiply through, we can get E sub CT is equal to EM and EF divided by the volume fraction of the matrix times EF plus volume fraction of the fiber times the modulus of elasticity of the matrix. And since we know this relationship, we can now rewrite it as the volume fraction of the matrix is just 1 minus the volume fraction of the fiber times F plus volume fraction of fiber times the modulus of elasticity of the matrix.